Okay, the next thing that we're going to talk about is the electric field produced by a single point charge. So we know that when you have a charge, you put a charge over here. What we've learned so far is that the charge is going to produce an electric field at every point around itself. So every point is going to acquire an electric field vector. So the question is, what is the electric field that a single charge is going to produce? So if I'm at a location R over here, at a distance R from the charge, I want to know what is the electric field that this charge produces at this location. That's what I'm trying to find out right now, right? So how do I do that? So what I can do is I can use this formula, F is equal to QE again. And so I can write E as F divided by Q, same thing. So E is equal to F divided by Q. So let's put some charge over here at this location that I'm interested in finding the electric field. And let's just call it Q test or something like that. It doesn't matter what I call it. So I'm just temporarily placing a charge over here, QT, and I want to find out what is the force on QT. And for that, I'm just going to use Coulomb's law, same thing that we learned at the beginning of today's lecture. So can you tell me, let's say Q is a positive charge and QT is also a positive charge. Can you tell me what is the magnitude and the direction of the force on QT? Let's forget about electric fields for a moment, go back to Coulomb's law, and let's figure out what is the force felt by QT.
K times Q times QT over R squared.
Exactly. That is the force felt by QT, right? So that's the F. That's the force felt by QT. I'm just going to draw it as a blue arrow. And if they're both positive charges, that it will be a repulsive force in this direction. So now that I know what the charge is and I know what force it's feeling, I can use the formula F equals QE to calculate the electric field. So the electric field is going to be F divided by Q. So it's just going to be F divided by QT, right? Because QT is the one that's feeling the force F. So F divided by QT by definition is the electric field. And so it's just going to be KQ divided by R squared. Everybody clear about that? So what we found is the electric field at this location. I'm going to draw the electric field vector as a yellow arrow. So the yellow arrow electric field has been produced by the charge Q at that location, right? And that electric field is pushing the charge QT and making it feel a force F. So we sort of went about it the other way around. We know what the force F is, and then from there we figured out what the electric field must be in order to produce that force. And we got this extremely important formula. The electric field produced by a point charge produced by a point charge at a given location is given by this formula. E is equal to KQ divided by R squared. Let's make sure we 100% understand what this formula is telling us. If I have a charge Q at this location here, and I want to find out what electric field it makes somewhere over here, and this distance is R, the answer is just KQ over R squared. So K is the same K that we had in Coulomb's law, KQ over R squared. And you can see that if the charge is positive, if this is a positive charge, it's going to make an electric field which points away from itself. And if the charge is negative, it's going to create an electric field that points towards itself, right? So E is equal to KQ over R squared. And you have both the magnitude and direction of the electric field produced by a point charge, right? So that is how I'm able to draw electric field vectors at every point in space. That's what I was doing earlier. So if I have, I'll just draw a separate diagram. If I have a charge Q right here, and I want to draw, what is this? Okay, if I have a charge Q right there, and I want to draw an electric field over here, for example, how would I draw it? And it's a positive charge. So what direction should I draw the electric field produced by this charge Q at the point A?
Away.
Yes, exactly. It's a positive charge. Positive charges always create electric fields pointing away from themselves. And at the point B, the electric field produced by Q is going to be in this direction. That makes sense? And also, if I want to be accurate, I should draw longer arrows for larger electric fields closer to the charge and shorter arrows for electric fields away from the charge, because the electric field is given by kq divided by r square. So if r is large, the electric field is small. That makes sense?
I have a
All right.
question.
Yes, go ahead.
So when the Q is positive, the charge me away, right? Is
The
that
electric, yes, go ahead, Yeah.
is that because we're assuming like the point A is positive as well, or is
No,
it just
the
that
point, point A is just a point in space. It doesn't have any
Oh,
positive
okay.
or negative aspects. It's just a property of electric fields, of charges, that positive charges always produce electric fields pointing away from themselves, and negative charges always produce electric fields pointing towards themselves, right? Okay, we'll see why that property is necessary. We can see that right now, right away. Suppose I place a negative charge at the location of A, and it's an excellent question. So it ties into what we just discussed a moment ago. Suppose this charge was Q1, and I place a negative charge minus Q2 at the location of A. And A is just a location in space. It doesn't have any properties at all. Now, forget about Q1 for now. You know that Q1 produces an electric field at A. So now you can see the direction of the electric field at A, and just focus on the point A for now. Oops, just trying to erase this. You can see the direction of the electric field at the location of A. You can also see the sign of the charge at the location of A. So now let me ask you the same question that I asked a little while ago. What is the direction of the force on Q2? So it's sitting in an electric field which is pointing up and to the right, and it's a negative charge. So what direction is the force on Q2?
Down to the left?
Exactly, because a negative charge will feel a force opposite the direction of the electric field. And so Q2 is going to feel a force in this direction, which is exactly what we expect. Q1 and Q2 we know are going to attract each other, right? Because they're opposite charges. So Q2 has to feel a force towards Q1, right? And that's why we need the property that a positive charge will always produce an electric field pointing away from itself, and negative charges will always produce electric fields pointing towards themselves. That makes sense? All right. Let's look at another example. That was an excellent question, by the way. It really, I'm glad that you asked that. Otherwise, I would not have mentioned this. Okay, suppose I have a charge Q1 over here. Maybe it's a negative charge. And let's think about what kind of electric field it's going to make. So consider a point A in space over here. How should I draw the electric field vector due to negative Q1 at location A?
Inwards?
Yes, exactly, radially inwards. So no matter where I consider the electric field, it should be pointing towards Q1. Everybody clear about that? So every point, a Q1 produces an electric field which points towards it. And strictly speaking, the arrows closer to Q1 should be made longer, and the arrows away from Q1 should be made shorter, because the magnitude of the electric field is given by this formula E is equal to KQ divided by R squared. So E gets weaker as you go further away. All right, let me just show this to you with a nice animation, the same animation that I had over here. Okay, so I'm going to turn off this sensor. So okay, let me just actually keep this sensor for now. I'm putting a negative charge over here. Notice that every point in space has an electric field arrow pointing towards it. That makes sense? That's what negative charges do. They create electric field vectors pointing towards themselves.